Hello, this video is entitled Line Integrals. Now, the idea of line integrals might be a little misleading. The word line, at least anyway, is that maybe curve integrals would be a more accurate term, is that we are integrating across a curve path, instead of, integration we've done across area regions or volume regions. We're essentially integrating across a curve path, plane curve or space curve, sort of like this picture right here. All right, so now let's see what we have here. Okay, there's your basic R of t definitions we've seen before, back in vector valued functions. So we have a plane curve and a space curve. Now we have a theorem that's the evaluation of a line integral as a definite integral. And you're going to see some other line integrals come up. There's different ways to do this depending upon how the problem is presented to you. So it's not too confusing, but this particular formula works given this situation. So let F be a continuous region on a smooth curve C. C is given by either xt or yt, like back up here, or xyz, where A is between t is between A and B. So it kind of gives you your limits of integration here. And then we have the following integral. And the C, they use C as a common notation there for line integral. Once again, C probably kind of means curve. Okay, let's see. So fxyz ds. See, so now instead of either dA here or dV, like we've had before, multiple integrals, we have ds, and it's just going to be one variable. It's going to be parameter t. And let's see what it says. ds is, talks about moving along the curve, not the x or y axis. ds is sometimes called the line integral because of that, the line integral of f with respect to arc length. Because notice this this ds right here in this particular form is the the magnitude of r prime, which is how we figured out arc length before for vector valued functions. It was integrating the magnitude of the arc length. Now we have to substitute x of t, y of t, z of t, because everything's going to be just one variable here. Everything has to be converted to t, so all the original x, y's, and z's must be converted to t. And so let's give this a whirl in this particular form. Now, before we do that, though, I want to show you, a lot of times, the problem will be given the parameterization or given what we need to do here, but I want to show you, just so we can learn how to do this, and this is just one particular example, if you had to create a parameterization. Now, this one is a little bit more involved, because we're having to find a parameterization across this entire path instead of just one little section here. So when you have it across a path like this, you have to treat each piece separately. So starting from the origin, I'm calling this one C1 right here, and then C2 would come this way and C3 would come down. So starting with y equals x squared, based on what we've learned before, is you can parameterize that by letting x be t, and therefore y equals t squared. So that will be our vector valued function for y equals x squared. And we'll send that from 0 to 2, because when you get to 2, obviously that'll be 2, 4 right there, so it makes it to this completion point right here, 2, 4. Now, to go left from here. Now, when you finish, whatever you finish your t with, you have to start with that t for the next one. You can't go back to 0. You have to start. If you finish with 2, you start with 2. So we'll have to make our parameterization work on the fact that it's based on 2. Now, here's some little tricks on this. Now, you can see that as we go across horizontally to the left, y is always going to be 4. But you see that x changes. So that means we'll have to have our variable, t will have to be in there. And here's a little trick that if x is going in the negative direction, that means the coefficient of t will be negative. If it's going to the right, it'd be positive. So with going vertically, if it's going vertically up, that means y will be a positive t. If it's going down, it'll be a negative t. So automatically, this is going to be a minus t. So to figure out what went in front here, I just had to figure out, okay, I know I'm starting at 2, so basically, and I need to be, t is 2, and the point value is 2. So basically, I had to say what number minus 2 would equal 2, and it would be 4. Because 4 minus, you put this 2 into t, and that will give you that 2 right there. And of course, 4 is already accounted for. Now, as far as knowing where t stops, it stops right here, but how do I know that that value is 4? Okay, the way I would do this is look and see, all right, what point am I at? I'm at 0, 4. So if I need the x to be 0 to plug into here, t would have to be 4, right? Because 4 minus 4 would give you that 0. So that's how I know it stopped at 4. Now, for the next one, I have to pick up at 4 again. And as I'm going straight down the y-axis, I know that x is always going to be 0, but the y will vary. So since this is going downhill, I know I'm going to have a minus t instead of a plus t. It'll be a minus t. Now I've got to figure out how to get this number in front. How do I figure that out? Okay, similar logic like I did before. It's going to be something minus t. I'm starting with 4, and for t, I'm starting with 4, and I'm at the point 4. So I've got to say what minus 4 would equal 4. And it would be 8, because you put in the 4 right here. 8 minus 4 will give me that 4 right there. And then to finish, I know I'm finishing at 0, 0. And so I have to let t finish at 8, because that way 8 minus 8 will give you a 0. All right. So I don't think we're going to get too involved in doing this, but I just wanted you to see how that was done. We're going to see a better technique called Green's theorem for evaluating line integrals across regions like that. That will be a little less involved, I think, or at least from the parameterization standpoint. Well, also, you won't have to do it in 3 separate pieces. So to work out a line integral, we'd have to do that in 3 separate pieces and add them together. A little bit tedious, so I wouldn't plan on making you do that on an exam. All right, now here's some function that we're going to evaluate the line integral. There's ds, and we're telling you it's the line from 0, 0 to 3, 9. I mean, you can get to 0. You can get from 0, 0 to 3, 9 different ways, but I'm telling you that it's a line here, so we have to work with it as a line. So that means, okay, easy enough. I got to come up with this equation from the line. Slope's going to be 3 because it'll be 9 minus 0 divided by 3 minus 0. So it's 9 divided by 3 is 0. The y-intercept is 0. So this equation will be y equals 3x. So that's the equation of the line that will go from 0, 0 to 3, 9. And that's easy to parameterize. I can let x equal t, and then y would be 3t. So there's my there's my vector valued function would be t comma 3t, and then since x is t, we know it's going from 0 to 3 right here. Now I'm going to need the derivative of t, because we're going to take the magnitude of r prime. So r prime ends up not having any t's left, so r prime will be 1 comma 3, and its magnitude then would be the square root of 10. So this part right here will be the square root of 10. Now we have to substitute. I'll scroll up here for a second. Because x is t and y is 3t, so everywhere up here I see an x, I'll put in t. Everywhere I see a y, I will put in 3t. Because see, we're reducing this down to one variable. That's why these are just single integrals. And you see it, so there's that square root of 10 from the magnitude I just pulled out, 0 to 3. And so you see there's x squared y plus 3xy cubed. So here's, like I was explaining before, I'm substituting the t's in right here. And I kind of combine these together a little bit. And I got 3t cubed plus 81t to the fourth. And that's pretty easy integral to do manually. It could also be done in a calculator too, but pretty easy. Just integrate them term by term. So that will be 3/4 t to the fourth, and then t to the fourth would be 1/5 t to the fifth. So it's 81 over 5 t to the fifth, square root of 10, put in 0, put in 3, put in 0. Kind of get this weird looking answer, but that's all right. Weird's not bad. So it's 79947 divided by 20 times square root of 10. Now what I'm showing you here without the square root of 10 is I'm just showing you that Maple didn't convert this one to fraction. Sometimes it usually will, it'll convert it when you tell it to, it'll do it, but it didn't for this one. So I used x instead of t, but this integral is just this integral here without the square root of 10. The square root of 10 is part of the answer, I just left it out of the integral. Because I just wanted to show that the calculator result was equivalent to 79947 divided by 20. And it was the same. That means I did the integration correctly. But the square root of 10 is definitely part of the answer. You might be thinking about these line integrals might seem kind of weird to you. One application is you can find the mass of a wire by using a line integral. Let's see, and we're also going to use line integrals to find work of a vector field here in just a minute. Now suppose this told you to do this by parabola. Take the path of a parabola instead of a line. This integral is actually going to be too complicated to work out. I just want to see if you understand okay with the setup of it for this one. The other one we could work out no problem. And so this one, if you say, because y equals x squared from 0 to 3 would get you to 3, 9, just like y equals 3x did. It would get you to 3 and 9. So if y equals x squared, just let x equals t, and then y would be t squared. So we have a different vector valued function here this time, because we're taking a different path. So instead of going from 0 to 0, 0 to 3, 9 in a straight line, we're now taking a parabola curve to get there. And take the derivative of the vector valued function. You have 1 comma 2t. Okay, I paused the video for a second because I decided I wanted to add a picture of a graph. No big deal really, but just kind of showing the blue one was the first one, the straight line path, and then there's the parabola curve in red. So I just felt like adding that in there. Anyway, we go back to this. So now we have a new magnitude because you have now 1 squared plus 2t squared, so it's a square root of 1 plus 4t squared. And then here I'm substituting now t and t squared in for, I should copy this down here like I did before. Yeah, this would be a good place to bring this into play. So I'll have to scroll all the way back up. That's the original function right there. So let me make it a little more visible down here. Yeah. Yeah, so now I'm substituting the x squared plus 3xy cubed, but it's different than the way I did it before because now we're putting in x, t for x, and t squared in there for y. So t for x means it'll be t squared, then that's already t squared. There's a t squared squared. But anyway, that's just the setup of what that integral would be. That would not be much fun to do because you would have to, I think it's actually doable. You know, some integrals aren't doable, but I think it could be done. You would have to split this up in two pieces, and then both pieces would require trig substitution. In fact, I'm going to pause this again, put this in Maple without the numbers, and just see how it integrates it. Okay, I switched over to Maple and typed in that integral. And you see it's a pretty big and scary result. But I'm looking through this, and the fact that I don't see any kind of, Maple didn't put any weird stuff in it. Sometimes it puts some weird function references that means it can't integrate it. But these are all, you know, proper algebraic terms, even the inverse hyperbolic. That's just a natural log form right there. But so that means it was doable. So, but you can see now what I was talking about, that it would have been highly unpleasant. Well, you know, I might have had fun trying it, but I don't know if you would have as much fun watching it. So, well, needless to say, we don't have to worry about that. And I'm saying trig substitution twice because you're splitting up the two integrals. Alrighty, let's look at this one. X squared plus y squared ds. And we're going clockwise, counterclockwise around the circle. X squared, y squared equals 4 from 2, 0 to 0, 2. So that sort of affects our path a little bit, the way we name it. Because remember these, as was talked about with these parametric things, the orientation, you know, can matter. So we have to set this up according to that proper orientation. Well, since you have a circle, that means your x is going to be cosine, your y is going to be sine, and then their coefficients will be the square root of whatever, basically whatever the radius is. So the radius of the circle is t, so it makes it 2 cos t, 2 sine t. And 0 to 2, 0 to 0, 2. Think of it like on a unit circle. That's going to go from 0 to pi over 2. All right. So let's get our integrals. Of course, we're going to need our r prime here too. All right, now we have, let's take the derivative of our vector valued function, which will be negative 2 sine of t, 2 cos of t, because we need the magnitude, and this one's going to work out really convenient for us. So the magnitude of r prime is going to be then 4 sine squared plus 4 cos squared, which equals 4, but that's the square root of 4, so which equals 2. So this 2 goes right here, 2 dt. Now when we substitute back up here, x squared plus y squared, we'll have 2 cos all squared makes 4 cos squared. 2 sine all squared makes 4 sine squared. So 4 cos squared plus 4 sine squared equals 4. 4 times 2 is 8. So look at our integral. All we're having to integrate here is it reduces down to 8 dt, which will just be 8t. And then you put in the pi over 2, and it will equal 4 pi. Now let's talk about line integrals of vector fields, which is how we'll find the work done by a vector valued function. Or I mean work done by a vector field, excuse me, not a vector valued function, work done by a vector field. All right, well, obviously a vector field means it's a vector. So what we're going to have is we still need our path, our curve path, R of t, because we need to know, we're doing this field along, assume it's moving along that path. And I just mentioned that it was going to equal work. So basically, to find this, it's a matter of evaluating f dot dr. Now, for the vector field, you will have to substitute the r, which r is going to be, maybe it doesn't have the z, but I'm just assuming maximum variables here. Because if it was plain, if it was instead of space, you would just drop the z. So it's going to be x of t, y of t, z of t. So meaning that these are all going to be functions of t that we substitute, like we just got through doing before. Except it wasn't a vector field, it was just a function, but we still had to substitute. But this is a vector. And then our vector valued function, of course, is a vector. And we'll take the derivative of it. We won't take the magnitude. We'll just take the derivative of the r prime, which will be a vector. And then we dot product. So that's what's going to turn this into a scalar, because obviously these are numerical results. They have to be scalar. So as soon as you take a vector and you dot it with another vector, you then have a scalar function of t, and then you can integrate that scalar function of t, plug in your a and b, and there you go. Not too bad. So here's another circular one. Same one as the one we just did, except the path is longer. So it's still 2 cos t, 2 sine t, because the radius is 2. And then this time we're going a little farther, so we're going from 0 to pi. Because it's coming all the way around here. And then here's the same derivative, so it'll be negative 2 sine t, 2 cos t. But we're not finding the magnitude. Oh, well, here's where it explains it right here, excuse me. So just that we gave you the picture, but telling you it's the semicircle. So basically it's x squared plus y squared equals 4, but it's only half a circle. And then from 2, 0 to negative 2, 0. So it did explain it, so that way we didn't have to have the picture, because it gave us the information that we needed to get everything we need to get the 0 to pi, and then to get the r of t. Now here's the vector field, which I just converted over to component form. I didn't want to leave it in I and j. So it's going to be negative y, negative x. So here's what your x and y are right here. Be careful not to use the derivative terms here. Make sure you use the original. So negative y then will be negative 2 sine t, and then negative x will be negative 2 cos t. So negative 2 sine t, negative 2 cos t, that is your vector valued function as a function of t, and then we dot it with r prime of t, and that will give us what we need to integrate from 0 to pi. Now this one's a little tricky. The way I did it is certainly a more efficient way to do it, but it might not be easy to see this. But when you dot it, you're going to get 4 sine squared minus 4 cos squared. Now, yes, you could have used both those identities we've learned before to integrate these. You could have rewritten sine squared t as 1 minus cos of 2t all over 2. I could have written cos squared t as 1 plus cos of 2t all over 2. But what I did was I recognized the identity here. So if cos squared minus sine squared equals cos of 2t, I knew that sine squared minus cos squared, if you reverse them, is just the negative of it. And of course the 4 is just the coefficient there. So the 4 goes right over there. So I just happened to notice this, and that's an easy term to integrate right there. But you could have done it if you had not noticed that little shortcut. Yep, got away from me. And then, so we're going from 0 to pi. The antiderivative of cosine of 2t would be 1/2 sine of 2t with a negative 4 there. So I'll put the negative 2 in there. right here, but then sine of 2 pi is 0, sine of 0 is 0, so actually you get a result of 0. You can actually get work with technically with 0 or even negative, because a lot just depends on, not that you have to see it visually, but what kind of vector field is it working against you. Really difficult, putting more force against you. You're actually doing either none or sort of negative work, really. But so it's okay to get weird. Just in other words, I'm saying it doesn't have to be a positive answer for this, like it does for area or a volume or something like that. Now this next one, okay, don't worry, I'm going to show you this, but obviously don't worry about doing it this way, because I'm basically saying I've already done it the best way, most efficient way possible. But you could have gone right back up here for this y equals 4 square root of 4 minus x squared. Since we're only looking at the positive square root, that's why this works. With more than half that circle, this wouldn't have worked. So I let x equals t, and that means y equals the square root of 4 minus x squared. And my integral goes from negative 2 to 2, because now we're looking at x values instead of trig values. All right, so let me just kind of blow through this real quick here. So when you substitute, so negative y is this, the negative of this radical right here. Negative x will be this. Then I took the I guess I didn't show the derivative, but the derivative, 4 minus t squared to the 1/2, you'd bring the 1/2 down, and then the exponent becomes negative 1/2, and then the derivative of the inside would be negative 2t. So 1/2 times negative 2t makes that negative t, and then the negative 1/2 exponent just drops it down to the denominator of a fraction. Then the dot product will yield me these two terms right here. So I got a common denominator, and I ended up not even integrating this one because it would have been too messy. The second integral would have been arc sine. First one, we would have had to probably use some sort of trig substitution. So I got a common denominator up and down by the radical here, and cleaned all this up and got this integral, which I just reversed. I don't know why, but 2t squared minus 4, square root of 4 minus t squared, from negative 2 to 2. Oh, turned out being 0. So it did yield the same answer as the other way. So you could have gone that route, and you still would have been okay if you didn't do the trig. I guess it wasn't as bad as I thought it was going to be this way, but I still like the trig way better. But now here's a space one. Now this goes back to what we learned in material for that first test, how to come up with parametric equations of a line. So remember, you subtract. So 5 minus 0 makes 5t. 3 minus 0 is 3t. 2 minus 0 is 2t. So starting from 0, 0, 0 just means it's, in other words, there's no numbers there with it. In other words, 0 plus 5t is just 5t. 0 plus 3t is 3t. 0 plus 2t is just 2t. So there's, earlier on when we did them, we'd have like maybe 1 plus 5t or 3 minus 3t. But no, since we're starting at 0, 0, 0, we don't have that. Of course, t will start at 0. That's easy enough to see, to make it 0, 0, 0. And also t would be 1 to get you to the 0.532. So it's going to pretty much go from 0 to 1 as your integral. So here's my vector field. So all I'm doing is plugging in these x, y's, and z's, according to this, right here, here, and here. So it ends up being 6t squared, 10t squared, 15t squared. I'm going to dot that with this derivative right here, 532. And I get 30t squared plus 30t squared plus 30t squared equals 90t squared. Okay, so that kind of cleaned up really nice. So all we're doing is integrating 90t squared from 0 to 1. And the antiderivative of 90t squared, because it's t cubed over 3, 90 over 3 is 30. 30t cubed from 0 to 1 will just produce an answer of 30. So this isn't too bad. Just keep, I like to make sure I keep the integrals. So this was a force field. Vector field was considered a force field along the given path. Doesn't really have any units associated with it or anything. So now here's a form when you see it written like this. When you see a dx, dy, dz, that essentially, when you see it in that form, that's sort of saying it's the dot product's kind of already done for you. It's like the dot product's already there. Because, dx, dy, dz are the derivatives, for r prime. But when I say dx, dy, dz, they have to be in terms of t, though. So like I said, you just kind of see it written in this form. That's how you, well, this one's a little bit different because it's not written in that. Well, yeah, I'm talking about right over here, excuse me. So this shows that it's already in differential form because it has the dx and the dy. So it's giving us a parameterization here, which that's essentially your r, but you don't have to, when you're doing it like this, you don't have to write it as r. From 0 to 1, but we do need both those derivatives. So the derivative would be 2 dt, and the derivative of this y would be 10 dt. So we substitute, y and x as they're defined up here, and then we'll be multiplying the dx here by 2, and the dy will be 10. I just kind of factored out dt from the whole thing because I knew I was going to combine the terms inside there anyway. So 3y will be 3 times 10t minus x, which is 2t. dx is 2. Y squared and let's see, it's going to be 10t squared, and then dy is 10. So you clean all that up, and you end up with this right here. 56t plus 1000t squared from 0 to 1. And pretty easy, 28t squared. And then 1000 over 3t cubed. 0 will be 0, put in 1. You get this, and then 28 would be the same thing as 84 over 3. So 84 over 3 plus 1000 over 3 would be 1084 over 3. All right, that's not too bad. Here's another one. Taking an arc path here from 0, 0 to 4, 8. Now they're not telling us we're having to parameterize this ourselves. So no problem, we just let x equals t, and therefore y will be t to the 3 halves. And to get your limits of integration, since we know that x equals t, and then x is going from 0 to 4, that means t goes from 0 to 4, because t is x. So here's the derivative is going to be 1 for this one. And it's going to be 3 halves t to the 1 half here. And then we just plug everything into right up here, and we'll see what happens. So x is t, so we got 2t minus the y, which is t to the 3 halves, times that 1 dt, plus the next part, x is t, 3 times t to the 3 halves, and then that's multiplied by the derivative of y, which is 3t to the 1 half dt. And you kind of end up with some loose terms here. Now when I expand all this out, notice that I have a couple of like terms I can add together before I integrate. So, negative 1 t to the 3 halves plus 3 halves t to the 3 halves will be positive 1 half just by adding their coefficients. So now I just integrate these 3 terms. Basically, I'm not going to go through all the steps here, but pretty easy. Do the antiderivative. Plug in 4, plug in 0. 0 will be 0. And 4 to the 5 halves is actually an integer number. it would be the square root of 4 to the 5th, so it's 32. So that's why there's no radical here, even though you got a half power, because the number 4 conveniently, has an integer square root. So anyway, that's all. You got to get a common denominator of, I guess, 5. Oh, okay, actually, when you cube this out, you'll cancel the 2. So 5 is the common denominator. But obviously, you can just put that in the calculator and do the math frac. It's going to be 592 over 5. Let's take a look at this next one. Also in differential form. So let's see what we have. See if that's yeah, it's the same. Oh yeah, it's from the same problem block there, so it's the same equation here because it covers both these problems, but we have a new path here. So 4 sine t, 3 cos t, from 0, 3 to 4, 0. Well, you put in 0, that's going to get you 0, 3. Pi over 2 will get you 4, 0. So it's elliptic looking, but not too difficult to figure out. So the derivative 4 sine of t will be 4 cos t. 3 cos t will be negative 3 sine t. Then we just kind of substitute. It gets a little messy here, but it's not too bad. And so put in a 4 sine t everywhere there's an x, a 3 cos t everywhere there's a y. We have dx and dy right here. So when you take this and you distribute this through here, and then you same thing with this, distribute this through here. Now you get they're not like terms, but you get a nice little thing here. It's because negative 12 cos squared t minus 12 sine squared t means you could factor out a negative 12, and that gives you cos squared plus sine squared equals 1. So that doesn't all go away, it just becomes negative 12. You don't have to integrate it. And these are like terms right here on the outside. So 32 sine t cos t minus 27 sine t cos t gives you 5 sine t cos t. So that all consolidates into 5 sine t cos t minus 12. I could convert this into a double angle, but I just went ahead and did u substitution. Let u be sine, let du be cosine, so that's easy. And convert the limits of integration. Sine of pi over 2 is 1. Sine of 0 is 0. So now for this one, we have 5 halves u, because this will be 5u du, so the antiderivative would be 5 halves u squared, 1, 0. And this one still stays in terms of, because you're just integrating 12. So antiderivative of 12 will be 12t. So for the first one, we're just going to get 5 halves. And then for this one, you're going to put pi over 2 in here and get 6 pi. I guess I could have got a common denominator, but there's no point unless you're having to pick an answer. The only thing that you really could have done here was multiply top and bottom by 2, and you would have had 5 minus 12 pi all over one single 2. But that doesn't really change the value, it just changes the way it looks. So, all right, that concludes this video on line integrals.